there. Welcome to another day of learning chemistry with Coach Powers. All right, today we're going to be talking about Jimmy Neutron. What is this? This is like a cartoon or something. We can't talk about that. All right, how about atoms? All right, we're going to talk about atoms. All right, for sure. If you want to watch Jimmy Neutron, that's cool too. So today's lecture is going to get into some of the theories that first helped us understand what the model of the atom was, okay? And I love this kind of stuff because what we have to do as scientists is often getting into things that we can't see, okay? So you kind of imagine things that you can't see, like a black box. If you had a little black box and you had something inside of it and you had to try to figure out what was inside, what would you do? What kind of experiments would you run to figure out what was inside? Well, that's what the atom is. The atom is like a black box that scientists can't see inside of. And yet we have come up with all of these really cool experiments to understand what it's like. And we've had to develop a lot of different models along the way. So today we're going to talk about a couple of those discovery processes. And if you think, in terms of what was it like to actually be the scientist that was going through and figuring out this black box, it's just absolutely fascinating. So I think you're really going to enjoy it. All right, so yes, we're talking about the atoms. And yes, Jimmy Neutron. If you guys want to go to that website, it's just a little clip of Jimmy Neutron in case you don't know who he is. This is a model of the atom we're going to refer to a little bit later. So I want you to kind of imagine what that looks like a little bit later, okay? So our objectives today are to summarize 5 essential points of a guy by the name of Dalton, his atomic theory, and then describe experimental evidence that helped us to come up with Dalton, Thomson's, and Rutherford's model. So first of all, I kind of want to show you this picture. This picture is a picture of atoms, basically. Now, each of these little peaks, these little bumps, those are the electric field of a single atom, each one. Okay, so there would be an atom, there would be an atom. These are atoms that are affixed to a surface, and a scanning tunneling microscope was able to dive down, look at those things, and see the electric field that represented them. Now, that's pretty amazing to me because when I was in college, this actually came up in 1990, and I went to college in 1989. I didn't know about this until I got out of college quite a while afterwards. But they didn't even have this type of technology as I was going into college. We couldn't see to the size of the atom. We had scanning microscopes, electron microscopes, but they weren't tunneling microscopes. And so we could see really, really up close things, but we couldn't see to this detail. So it's pretty cool to think about the fact that we can actually see to the size of an atom now, because we didn't used to be able to do that back when I was in school. We made a lot of progress. All right, so there was a guy by the name of Democritus. Okay, now Democritus was a Greek philosopher around 400 BC. And he actually is the one that is oftentimes given credit for the word atom that we come up with. He had a mentor by the name of Leucippus that some people dispute whether he was really alive or not. Was he real? I don't know. And supposedly Democritus might have got some of these ideas from him. One way or the other, this is the guy that we typically attribute to the idea of the atom. Atom, A, meaning without, tome, meaning to cut, so without cutting. Atoms, that's basically what atom means. It's you can't cut it. It's the smallest part of an element that can't be broken down into smaller particles. Okay, and we have to remember that Aristotle was the main philosopher of the day, and Aristotle actually believed that you'd be able to infinitely divide things up over and over and over again, just forever. Okay, so Democritus and Aristotle kind of had some conflicting viewpoints here. Aristotle's idea is the one that took off. Democritus's idea did not take off. Aristotle's idea was basically the most prominent thought in our world all the way through like the 1600s or something, maybe the 1700s even. So eventually people started looking at more experimental evidence. And there's a guy by the name of John Dalton. And Dalton was kind of an amazing guy himself. He was an English teacher, okay, at the age of 12. Okay, when I say English, he was from England. And so he was teaching school in England at the age of 12. That's when he became a teacher. And he did a lot of experiments in his life as well. But, one of the cool things about Dalton is not only did he do experiments, but, sometimes people can be really amazing and really famous and make great contributions to society because they're synthesizers of information. They take information that other people have, come up with, and then they pull them together to come up with the main idea. And that's what Dalton's atomic model is all about. Okay, his model of the atom basically is a compilation of other scientists' model. Every element is made out of tiny particles called atoms, all right? Well, there's Democritus's idea. Atoms are indivisible, they cannot be broken down, right? Sorry, that's Democritus's idea. Atoms of the same element are identical, okay? Every Cu atom is exactly like every other Cu atom, all right? Atoms of different elements can join together to form compounds, all right? Then we have a couple different theories here, law of definite proportions, law of multiple proportions we're going to talk about. So basically, H2O here on Earth is going to be the same as H2O on Mars. They're exactly the same. That's the law of definite proportions. And CO and CO2 are always made of the same mixture of whole number ratios of the carbons and the oxygens. That's the law of multiple proportions. Atoms, number 5, are arranged in chemical reactions. So they're rearranged, right? This is the law of conservation of mass. This is a guy by the name of Lavoisier contributed greatly to that. A guy by the name of Proust contributed to one of these others. Dalton actually did one of them, but other scientists were all involved here. So here's this idea that we could take methane and oxygen, bring them together, and create carbon dioxide and water. So new arrangement of atoms. Okay, so that's Dalton's 5 basic tenets. Okay, now. Number 4 and number 5, basically all of these are starting to be accepted based upon experimental evidence. But in particular, looking at the law of definite proportions, water always has the same proportions of hydrogen and oxygen by mass, okay? And you can see an example here of salt. No matter if I have 200 grams of salt or 100 grams of salt, that I'm going to have the same ratio, the same percentage of salt, sodium to chlorine. And law of multiple proportions, already talked about that, that you'd have similar ratios of these carbons and oxygens. And, this stuff kind of might seem to be really common sense to you and I, but again, they had not even a clue as to what an atom was. They were figuring this stuff out when they hadn't even understood what an atom was, okay? So it's pretty amazing, the black box that they were looking inside, all sorts of really cool experiments that you could do some more research on to figure out how it is that they guessed, that this actually was a thing. What evidence did they collect to say that this was true or that this was true? Pretty cool stuff. But again, Dalton had a lot of these concepts, and, it's kind of also important to remember that, basically 3 of these aren't necessarily true anymore, the way we look at them. For instance, we know now that number 3, we can have isotopes. We have different numbers of neutrons, not exactly identical. We know that we can divide atoms now, right? So you can cut them up into even smaller pieces into protons, neutrons, and electrons, quarks, and you can keep going deeper and deeper. And we know that that you can, break things up according to nuclear reactions. So anyway, cool stuff. But we find out that there are some changes as time goes on, and it's okay. It's okay for models to change. In science, models are changing all the time. So Dalton's model was basically this. He basically had this idea that an atom was a solid sphere, kind of like a billiard ball, okay? And so kind of get this idea. Dalton's model was basically a solid sphere, and each atom was going to be unique to each different element. But then a guy came along by the name of Thomson. And Thomson was doing experiments with a cathode ray tube. Kind of cool stuff. Okay, so here's a cathode ray tube. And you might be like, well, that looks like a fancy little device. Yeah, it's pretty fancy, I guess. It just is basically a piece of energy that's shooting through. And we now know that this piece of energy is called electrons. Back then, we didn't necessarily know what they were. But notice how this little green line is slanting downward. Now that green line would slant downward toward toward a positive charge or away from a negative charge. And that told Thomson something pretty interesting. That told him that whatever was making up this green line must also be negatively charged. It also helped him to understand that there was mass, because they put a little flywheel inside there, and they actually saw that when these little particles hit it, that it was actually churning that little flywheel. Now, like I said, this is kind of a fancy, fancy device maybe, but we actually have them. We have one right in this room. It's a cathode ray tube, is what the old TVs, the old computers used to be made out of. Okay, so I'm going to go turn on TV over here. I'm going to show you something kind of interesting. So I'm going to move this along. want to show you this TV. Okay, and one of the other things that was affected by a zoom up a little bit more. One of the other things that affected this cathode ray tube was a magnetic field. Okay, so I'm going to turn this on. Now, this TV has a cathode ray tube in it. Okay? And what I want to show you is that this magnetic field that I have in here can actually affect the way the electrons are moving. Okay, so I'm basically bending the electrons right now. Touched it, you saw it's kind of stayed green for a second, right? So I just messed up that TV pretty badly. I always try not to touch the TV because you can permanently ruin these. I don't know that I permanently ruined it, but I may have. And you can see though that you can create a really cool colored effect by making these little electrons inside here change their actual orientation. Okay, it looks like it's come back to normal, so I think we're going to be okay. But isn't that really fantastic? So that's a cathode ray tube. Old school computer monitors and old school TVs were made with cathode ray tubes. So Thomson is given credit for discovering the electron. He believed in what we call the plum pudding model now, that there was a positively charged goo, that these negatively charged electrons were all kind of, embedded throughout. Okay, so basically his model was that it was kind of like bread pudding. So imagine there's your atom, and you've got these negatively charged electrons, negatively charged little particles, and they're embedded inside this goo. Okay, if you guys have ever had like bread pudding, well, this plum pudding is what we know kind of today as like bread pudding. They call raisins plums, and so it's basically raisin pudding. And so you've got this positively charged goo, and then you've got these negatively charged electrons that are embedded inside of them, right? And so these are all solid little particles, and they have mass, and they're inside this goo. Okay, so that was Thomson's idea of the model. Okay, he believed in that model. And so as scientists continued to do more research and continue to learn about things, some scientists were testing this idea, seeing if this model seemed to be good. Because remember, we can't see inside of it. So a guy by the name of Rutherford, Ernest Rutherford, came up with a really interesting experiment that we call the gold foil experiment. And his experiment was testing Thomson's idea. He said, okay, well, if this middle of the atom is made up of goo, then if I take these radiation sources called alpha particles, which are basically the helium nuclei, 2 protons and 2 neutrons, and I shoot them at this goo, then they should be able to just go right through, because these particles will be way bigger than the electrons. It'll knock them out of the way. It'll just go right through the goo, right? But we'll show you the picture here in a second. He found out that wasn't actually the case, that the nucleus was this positively charged, dense, really small center, okay, that's going to contain, and he didn't know what they were containing at the time. He just knew they were positively charged. Today, we know that there's protons and neutrons, but we just knew that a nucleus was there. That was his model. There was some sort of nucleus that was positively charged in the middle. And most of the atom was empty space. That's kind of cool. It's kind of, imagine like if you're in the middle of Mile High Field. It used to be Invesco and then Sports Authority, and now it's Empower. It just keeps changing names, right? But the middle of Mile High Stadium, okay? And you put a little marble in the middle of that. Then the outside area where all the fans are going to be sitting in the farthest, highest bleachers, that's the outside limit of the atom. Very, very, very far away, and that's where the electrons are flying. If you have a marble-sized nucleus, it's really small. Now you and I are made up of these small little particles, which means that you and I are mostly empty space, because we have these tiny little marble-sized, things inside of us in comparison to where the electrons are at the outside of the stadium. That means we're mostly empty space. You and I, mostly empty space. Kind of wild to think about, right? It's kind of cool. And then other atoms, other matter is mostly empty space. So here's this experiment. Really, really cool. All right, so alpha particles shooting at a little piece of gold foil. Just imagine tin foil, but made out of gold, okay? Aluminum foil made out of gold. Now, again, according to Dalton's theory, everything should pass straight through because it's just a goo, a positively charged mush. Well, it didn't pass straight through. It actually had some of them deflect to the side and some of them bounced back. Now, Rutherford, when he saw these little photographic developments, this was X-ray paper lining this, and he saw these little photographic developments on the inside of this, he said, it was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell, like a howitzer shell, at a piece of tissue paper, and it came back and hit you. Now, that kind of sounds a little crazy, but it was crazy to Rutherford. Imagine a 15-inch shell, okay? So something like rocket size. It's got to be huge, right? Something that would shoot out of a rocket-sized, gigantic howitzer type of, cannon, and you shot it at a piece of tissue paper. And all of a sudden, instead of that thing just destroying and demolishing, it went right through the tissue paper. It bounced back. It's not at all what Thomson's model had been predicting. So Rutherford had to come up with a new model. Okay, the deflection was due to having like charges repel, so positive charges would come because the alpha particle is positive. The positive charges would come in contact with, or not contact, but come very near other positive charges, and they would push away. Okay, so alpha particles coming in vicinity of a positively charged gold nuclei, so they would push away. But then some of them would actually hit the nucleus and bounce back. Most of them went straight through. Okay, most of them went straight through, but there were these exceptions. So the model needed to be adjusted. And so, again, the typical Rutherford model would be kind of like, all right, well, I've got this nucleus in the middle, and it's got solid, and it's small, and it's positively charged, right? And then I've got these electrons that are moving around on the outside of the atom. This is kind of like your typical Jimmy Neutron type of, atomic model, that you've got these other guys flying around the outside, and that's the electrons, and then the nucleus is a dense, very small, positively charged part of the middle. Remember, electrons are negatively charged, right? So these are flying around the outside. And so if these electrons are zipping around really fast and crazy, what would keep them on the atom? Why would they stick around instead of fly off? Well, because negatives and positives are attracted to each other, right? That's the electric force, right? The attractive force between positive charges and negative charges. Opposite charges attract. And so that's what keeps those electrons in the vicinity of the nucleus. So let's look what we learned today. We learned that if you look at Dalton's atomic theory, you should be able to summarize those 5 essential points. Okay, basically showing, that he had taken all this other interesting information that people had collected and synthesized it into one main concept that we still use today. And even though we now know that there are certain parts that aren't true, it's still a useful model that we can adapt and use for our common everyday talking as we even develop an understanding what the atom is like and how we understood it back then. And then, can you describe experimental evidence? Yeah, so like Dalton was doing experiments with carbon dioxide and carbon monoxide, I believe it was. Various different types of gases, or maybe it was hydrogen and oxygen he was doing experiments with. But that they were able to use experimental evidence to figure out stuff like laws of definite proportions, right? Thomson did the experiment with the cathode ray tube, and then Rutherford did the experiment with the gold foil. And so gold foil experiment, cathode ray experiment, the plum pudding model, the classic nuclear model, the Jimmy Neutron model, all right? And then Dalton was more like that billiard ball, solid little sphere. So yeah, I think you've got a good feeling for what the basics of the atomic model were like. There's a lot more scientists that contributed to this model. People like James Chadwick, who helped us understand what the neutron was. You've got people that were helping us understand the size and the charge of the electron. You've got all sorts of scientists that were doing a whole bunch more cool things, and we'll learn more about those when you actually take chemistry. But this gives you a good idea of the basics, and really neat to look inside that black box, right? How did they figure this stuff out? Well, really cool experiments like the gold foil experiment and the cathode ray experiment helped them to come up with models and ideas of what was inside the atom when they couldn't even see it. You're going to need to do that for your life. There are going to be things in your life that you're not going to necessarily understand, but apply some of the scientific method, apply some experimentation to some of these things, and it might help you to understand some of these black boxes that you discover in your life. Yeah, so I hope you can take this and use it someday to become great scientists, great people, and remember to do great always. Be kind to others. God bless.